So 2.1 is looking at the rate of change. So one more time, this is a small chapter. It's a little concept. It's not heavy on calculations. It's not heavy in terms of concept calculations. It's heavy in terms of little calculations. You're going to need your calculator. So maybe take your calculator out. And it's rates of change. Okay, so we're going to be punching a bunch of numbers into a calculator to calculate a bunch of stuff. So calculators out. All right. Rates of change. We've done rates of change before. We had this unit or this topic way back in grade 9. So the rate of change is slope, right? So that's literally slope. So we're looking at the idea of slope. Okay, a rate of change is slope. So in grade 9, we said we were looking at rates of change. Rate of change is slope with a context, right? So it's got units, it's got meters per second, dollars per hour, stuff like that. So we said, okay, but it's slope with a context to it. So that's where we've heard that word before. You're like, I've heard rate of change. That's from grade 9. Okay, so we're still using the same idea, so it's slope. Today we're looking at the idea of a secant line. So a secant line, so today's kind of a lot of little definitions, reminding you of a little bit of grade 9 and 10 material, so bringing that stuff back. So secant line is a line that passes through 2 points on the graph of a function. So 2 points on the graph of a function. A secant line is the graphical representation of the average rate of change. So a secant line is the slope, the average slope. So the average rate of change, which is like the average slope. Okay? That means that if I was to take any 2 points here on this graph, and I said, okay, so I'm going to take this point, and then do a secant line between them, right? So do a secant line between them. Then this slope of that line is considered to be the average rate of change. I'm going to talk about like speed, velocity. I'm going to talk about that because that one usually relates better to what we're talking about, but that's just because we're bringing it back to what we started with in grade 9. We did a lot of distance time graphs. Now, this is this idea here. So when I'm looking here, I'm talking about the average slope, average rate of change between those 2 points. Stuff is happening in between it. Right? So it's not quite exact, but this is average. That's why they're saying between those 2 points, average, right? Close enough. This is considered to be a positive, right? So this one's positive. So this is considered to be positive, right? When it's sloping up to the right, it's considered to be positive, okay? When it's down here, so this one, if I do another one and I said an average rate, how about if I do it between this point and this point, and I said that average rate between those 2 points, this would be considered to be negative, right? So this would be considered to be negative, so negative average rate. So sloping down to the right, up to the right, okay? So positive slope, negative slope. And that relates back to, again, grade 9, right? So this section, we're looking back at a bit of grade 9 and grade 10 material, and we're going to kind of relate that back. And then what this does is that this chapter relates to how calculus developed, right? So that's why I need this definition, because when we begin calculus, if you do take the calculus course, it talks about this secant line and trying to get it more precise. This is where one of the calculations of calculus comes from. Okay, so we got the secant line. Now, when they say average rates, you might be like, no, but it is between those 2 points, right? So that's the average rate. So when I say average rate, it's between these 2 points. Something could be happening in the middle, but we're looking at the 2 endpoints to get the value. So that's kind of like the idea of if you're driving somewhere and you said, okay, it took me about an hour, I traveled this speed on average, I was driving at 60 kilometers an hour, right? And then your parents go, wait, how fast were you going when you passed the cop? You're like, oh, at that instant? Maybe a little faster, right? So instantaneous is what calculus is going to look at. It's going to be like at the instant that you pass the cop, how fast are you going at that moment? Not average rate. When I left the house, when I arrived to the cottage, that's how fast I was going. That's average rate, start to end. We don't look at kind of what's happening in the middle. There could be something happening. Instantaneous means at the instant. How fast were you going at that exact moment? So that's what this is leading to. So everything we've done when we do slope of a line requires 2 points, correct? y2 minus y1 over x2 minus, always 2 points. What calculus looks at is what happens if I have 1 point. I cannot do y2 minus y1. So then they developed a pattern. They looked at secant lines, what happens with that, and that's where this comes in. So we're starting with secant lines, and we'll eventually get to a tangent line. A tangent line means 1 point. Secant line means 2 points. So looking at secant line right now. Okay, so average rate means between 2 points on average. So that's why they say average. Okay. All linear relationships have a constant rate of change. Oh, hang on. So all linear relationships have a constant rate of change. So again, this is kind of warm up. We got to do a bunch of little definitions. If it's linear, we know it's a straight line, right? So it's going to be a straight line. So all linear relationships have a constant rate of change. That's just telling us what we already know. We know that the rise and the run, so if the rise here is 2 and the run is 3, right? We know the same rise and run will occur for the entire line. So it'll be 2 to 3. And then if you took the whole thing, that would be 4 to 6, right? So no matter where you go on this line, the slope will always be the same. So same rate slope, right, for the whole line. Whether it's 2 over 3 or 4 over 6, etc., it's the same slope. So we're going to get 4 over 6, 2 over 3, the whole way down. Okay, so for a linear relationship, we know that all linear relationships have a constant rate of change. So it's a constant rate of change. Does that make sense? Okay, so the slope of the line will be the same for the whole way, and we know that already. So as soon as you see a linear relationship, you know it's a constant. This is considered a constant rate of change, constant slope for the whole thing. Over different intervals, it will get the same result. So that's what this is saying, 2 over 3, 2 over 3, or you can do 4 over 6, which reduces to be 2 over 3. So over any interval, it will be the same. So constant rate of change. All right. And the next little definition here, or explanation, non-linear relationships do not have a constant rate of change, right? And we saw that above. So we saw that above with our non-linear quadratic. So will it have the same slope, the same rate of change? No, because looking at this, it's positive, look, and then if I took these 2 points, it's changing. Do you see how the rate of change is changing? Depending, if I took this red point and that blue point, look, it's a different rate. So depending on which 2 points I take, this rate of change will be different. Okay, so anything that's curved, anything nonlinear will not have a constant rate of change. It's only lines that have a constant rate of change. Make sense? All right, so then again, bringing back grade 9. We know that rate of change, that definition has not changed, okay? So we're not saying, oh, now new definition. Average rate of change, we did this in grade 9, is still slope. But we're using our newfound, right, grade 11, 12 notation to write it again. You probably saw M, lowercase. You must have seen M, lowercase. Lowercase, not uppercase, please. Uppercase is midpoint, right? So I use lowercase for M. You might have seen the delta y over delta x. We don't use a lot of delta stuff. The sciences like to use delta more, right? Delta means change. So this means delta, which means change in, right? It's the Greek, right? So when you say delta y over delta x, change in y over change in x, right? So you may have seen a teacher write it like that. We usually wrote it y2 and y1. y2 minus y1 over x2 minus x1. But now that you know all your beautiful function notation, I'll zoom in there, right? F at x2 is y2. F at x1 is y1, right? So they're just rewriting y2 minus y1 over x2 minus x1, our same slope formula, but using our new function notation. Is that okay? So f at x2 is y2, f at x1 is y1. All right. Questions? All right. Flip over to the next page, and I forgot to clip and paste the picture. So I will find the picture in the book. I meant to clip and paste it and then copy it, but I forgot to, so we're just going to find that. So right here, this question, I took it from the book, and I was using their graph, because they already have a nice little graph there, and I meant to clip and paste it, and I forgot, so I'll fix that later, but it's right here. It's page 71 in the textbook. So if you want to look, it's page 71 in the textbook, and it's right here. So basically what it is that we have Andrew, he's draining water from a hot tub, right? So looking at the words here. The tub holds 1,600 liters of water, so they have it graphed right here. It takes 2 hours for the water to drain out, so it's draining down. You can see the dots. They have the dots, but the dots are hard to read, right, because you can't read it accurately, so they have the chart as well. This chart are these dots, right, because the dots are not really accurate, so they charted it here. 2 hours to drain out completely. The volume in liters remaining in various times is shown in the table and the graph. So you can see from the graph it is nonlinear. You can see that the changes are not constant, right, so it's nonlinear. You can see also, right, it's got a curve to it. So what we're doing is answering the questions from this information, right? So I have the x and y, so x1, y1, x2, y2, so all the information is from here. Okay, sorry, and I forgot to paste it on the picture. I'll fix that for later. All right. Okay, so from there, then what we're doing is we're going to calculate the average rate of change in volume during each of the following time intervals. Remember, average rate of change is slope. So we're trying to find the slope for all of these little time intervals. And then we'll discuss. So there's a lot of little calculations. I'm going to go through them a little bit faster just because I have the numbers already here, so following along. But what we have here is that we want the slope, and it's y2 minus y1. So if you want, this is going to be f at 90 minus f at 30 over 90 minus 30. You can skip that step if you want, and you can go straight to this one and just show me your y. So it'll be 100. So at 90, it's 100, right? And at 30, it's 900. So I'm getting my x and y's from here. I'll just do it a little faster because I know you can read off of a chart. So 900. So you can skip to this step if you want. You don't have to show me f at 90. You can go 100 minus 900 and then 90 minus 30. Okay, and then we ran out of room. Again, I was anticipating I'm doing the calculation. So there's no calculation for this one. We're just plugging it in. And I got negative 40 over 3. And then always do units. For math, we like to put the units at the end, right? And it's liters per minute. It's always the y to the x, right? So we know from the chart it's liters per minute. Liters per minute, again, from grade 9. We're okay. And then just put the units right there. So I don't need to see a ton of calculations. This one, you're not calculating, you're just grabbing the numbers from the chart, right? So I'm going to do that 4 times. And again, sorry, I didn't put the chart above, so it's harder for you to follow, but I'm just going to put the numbers in for us. So I would put in, it's 100 minus 400 over the 90 minus 60. Are you seeing what I'm doing? It's y2 minus y1, x2 minus x1. Is that all right? Yep. Oh, it doesn't matter. You can have them both backwards as long as they match. So if I do 400 minus 100, it's 60 minus 90. Yeah, so as long as they're a matching pair. Yeah. Yeah. Is that okay? Sorry, just the chart's missing, so it's harder for you to follow. Okay, and then I'll just plug it in. So I got, this one I got negative 10 liters per minute. Okay, and again, I grabbed it from the chart, so it's going to be m equals 10 minus 100, and I got 110 minus 90, and then I got, oops, equals negative 90 over 20, so negative 9 over 2. Fractions, please. So leave it as a fraction. Always do fraction. Okay, leave it as a reduced fraction. We tend to like that better than going to decimals right away. Sometimes we'll go to decimals, usually money, right? We go to decimals, but other than that, we usually keep fractions. Okay, so just grabbing the numbers from the chart again. 0 minus 10, 120 minus 110. Is that okay? y2 minus y1, x2 minus x1. Grab and reduce. So it'll be negative 1 liter per minute. Okay, and then again, so it's y2 minus y1, x2 minus x1, right? And we're just grabbing it from the chart, and they matching pairs, right? So that brings you back from grade 9, haven't done that in a little while. And then here it's just y is the rate. So again, we're trying to bring back these concepts of the rate. Y is the rate of change in the volume negative, right? And what does negative mean? It means the water's draining out. So in grade 9, we would say the water's draining out, or we can say the water's decreasing, right? So water is draining out. Water is draining, draining out of the tub. Decreasing, so you can use the word decreasing. Some people might use decreasing in volume, right? Something like that. Any of those words to explain? Does that make sense? Right, so just explain why is it negative, because it's the water's going down. It's decreasing in volume. The water's draining out of the tub. Anything like that is good. Okay. Does the tub drain out at a constant rate? And we just discussed that in the other page. It's not constant. Since it is nonlinear. Okay, or you can say it's a curve. Okay, so you can say it's a curve or it's nonlinear. So as soon as it's a curve or nonlinear, it is not going to be a constant rate. An interesting note, I just put this on the bottom. The magnitude is a word that we're going to slowly start to use once in a while. That means the absolute value. So the magnitude of a slope. So the absolute value of the slope is getting smaller as time increases. Looking at the graph, right, and again, it's just kind of, oh, right, that kind of makes sense in reality, right? So looking at the graph, again, we don't have the graph on the page because I forgot to clip it. But looking at the graph, when you take a slope between those 2 points, see, if I took those 2 random points here, the slope is negative, right? If I took, say, these 2 points here, it's negative, but it's less negative, right? So slope is higher, and then see how it's doing this, the magnitude of it, not talking about the negative part, right? So without the sign, and then look what happens if I take these 2 points here, slowing down, and then what happens here? Well, the slope between these 2 points is even slower, and then look, so it's slowing down. So that's why. So it's an interesting note, and we'll look at that as well later on with, okay, what's happening with the slope? It's decreasing. What does that mean and stuff? Because look, when you're draining it at first, it's going out very quickly, right? So it's going out very, very quickly, and then as it kind of shallows out, there's less pressure on the water, and it's draining out a bit slower, which makes sense. In reality, it's not going to be a constant. So they're just saying, isn't that interesting that the slope changes? And then why and stuff. So we are looking at the slope. Yes?
Didn't you say it's not constant because like the slopes are all different as well?
Yeah, the slopes are different. The slopes are changing. Exactly. Right? So it's not constant. You can see the slopes are changing. We just answered that above. It's a curve. Exactly. Yep, that's a good answer too. Right? Because it's not constant. Constant means constant slope. Okay? All right. The next page, we're going to do the same thing, except this time I gave you an equation instead of forgetting to give you a graph. So either way, we didn't have the information. But this one, look, I gave you the equation. It's right there. So for this whole page, we are using this equation. So we're going to talk about the slope of this. I didn't graph it for you. So we get to sub in, right? I wanted to show you this just because I don't want to see. So remember in grade 9, we're like, show me the subs, show me the sub. I want to see the bracket. Show me every single step. Please skip some steps. I don't want you to show me every single step for the substitution now, because now you're grade 12. I don't need to see every little bracket because, oh, it's going to be so many substitutions. Thank you. Okay, so here, this is all I need you to show me. So you can just show me that you're subbing in, right, for the H. So I'm going to do this. So I'll show you kind of the only kind of steps that I need to see. You can do more if you want, but then this is kind of the minimum. So for this one, I'm going to do the slope equal. So I want the average rate of change, and then we're going to do this. Try to make sure that your line kind of lines up with this. Get in that habit, just because some people put the M way at the top, and it just, I don't like it because it's technically wrong. You do this M equals, and then you do the line here. Right? And then you do the whole thing, but this M is really floating way up. Try to put it in the middle. I'm not going to measure it, but look how I put the line first. Like I put the equals and I draw my line first. Then I know it's centered. right? That's going to be a habit you're going to need, again, if you take the calculus course, because we do these long questions that have a fraction on a fraction, and it gets harder to center it. So I do equals and put the line first. Then I'm always centered, right? Because I put the line first. Because like I said, we're going to have these long questions. We'll have fractions on fractions. So it'll be harder to center it because you go, oh, I missed, right? And missing actually mathematically is wrong, right? So when we get later, I will take off marks because when you're putting stuff that we were talking about later on, the equals is on the top versus the bottom, it gives a different answer. Okay, so try to center it. Here, we're going to just say h at 1 minus h at 0 over 1 minus 0. So again, that's y2 minus y1 over x2 minus x1. And just make sure they're matching pairs, right? So the 1 with the 1 and the 0 with the 0. So they're in the same order. So if it's the 1, 0, it's 1, 0. Okay? Then I don't want to see, so it's the opposite of what we told you before. I don't want to see you subbing in 1 with the bracket and the squared and thing. Just do it on your calculator. So actually just skip. It's the opposite. Just because it's so much writing, you can show it, but boy, it's a lot of writing because you can see I have to show it, sub, bracket there, subtract it. So if you want, I'm letting you guys, because grade 12, just sub it right in. Sub it right into your calculator. Go 5, 1 squared, so 5 times 1, negative 5. And plus 10 plus 120, there you go, 125. Okay, so we don't need to see the substitution. If you do want to show me, it's okay, but if you want to do it on your calculator, you can as well. You'll see why, because in the next ones, there's so many of them, you're going to be like, oh my gosh. Okay, so if you can, just go right to 125, so all I need is the 125. Okay, same thing for 0. 0 you can do fast, it's just minus 120. And then 1, oh, I didn't need to show the 1. You could have skipped that step, sorry. So then it's just 5 over 1, so 5. And then again, at the very last step is where I want you to put the meters per second, right? You don't have to show me units throughout. I know in science we show units throughout. In math, we kind of just throw it in at the end. Okay, so you can do more steps, but again, if you don't want to, you can use your calculator for a bunch of this. All right, let's try it again 3 more times. So m equals, and this would be h at 2 minus h at 1 over 2 minus 1. And for 2, I got 120. And then for 1, I got 125, which we just answered here. I don't need to show over 1. I don't know why I keep doing that. Bad habit. And then 5. Negative 5. Again, we got m equals